Hello, my mathematical friends. Today I want to introduce you to the idea of convexity, convex functions. We'll start with convex functions. In later videos, we'll talk about the more abstract and more, say, wider view of what convexity is all about. There are whole branches of mathematics that study convex objects. It's very, very interesting. And for now, why is it interesting? Well, it's an advanced idea in a sense, like you probably won't see it in high school or even in college math, but maybe later on you'll see more of it, maybe in calculus sometimes. But generally, people avoid this topic in school mathematics. Why, I don't know. It's like a really interesting topic. Convexity is really very cool and very interesting. And okay, so some other reasons. Another reason is, well, convex functions provide a very interesting mechanism to prove your favorite inequalities like MGM and so on. And they have a kind of a unifying principle or theory now behind them, and that theory is convexity. You'll see how it all comes together in a very, very beautiful way. And also, it's you can do your own personal research. You can, you know, why not? How do I spell research? You could choose convex functions and do all kinds of research. I'll show you some techniques and ideas, some basic stuff, and you can take this in your own direction. I'm sure you can discover your own implications. There's probably many things that you can look into and discover. So let's get to it and get into what exactly do we mean by convexity. So here I have an example of a convex function, and we are going to say that it's convex in, say, the interval x1 to x2. So here is x1, suppose here, and here is x2. So f of x is convex, and I will call this convex up or convex upwards, okay, on this interval x1, x2, if the following property holds. So I choose any 2 points, A and B, and I go up here and I have this point here. This is A, f of A. I can call that A, and move up here. This is B, and this is B is little b, f of B. This point, big B here, like this. Okay, and I draw a line between them, a chord in between them, and notice the chord is above the function f of x. So that's quite interesting. So if I always have this property, let's say I'd move A over here and B over here, so I have another chord like that. So A, B, it's again above f of x. So any chord, so for any points here, a greater than, less than or equal to A, less than or equal to B, less than or equal to x1. So A and B are in this region from x1 to x2. And if for any A and B that we choose here in x1 and x2, if the chord AB is above the arc AB. Okay, so this is the chord AB here. And the arc, well, that's along this curve here. If the chord AB is above the arc AB, then f of x is convex up. Call it convex. Some people just call that convex. Some people call it concave, actually. But in some books, I've seen the opposite. But I call it convex up, and I think this will help disambiguate everything. This looks like a good definition, like it's a good intuitive definition, but it's not perfect because it doesn't take into account a straight line. You can see that this definition sort of leaves straight line in limbo. What do we do if function f of x, let's say, is a line? Then what? Okay. Well, I don't want to leave this case out, so let's modify this statement here just a little bit. This statement is okay, but I want to make something that will take into account the edge cases. So what we'll say is the chord AB is not, or no part of the chord AB is below the arc AB. Now, this is a good definition. This is really good because under this definition, a straight line is also convex. It's convex up. So very good, very good. And what about this related case here? Hang on. Yeah, what about this function here? Let's say we have f of x here. So between region here, x1 to x2, this is our interval. I choose any two points and I go up like this. Now my arc is below my, my chord is below, the chord is below the arc. Well, this is, some people call this concave, but I don't really like that word. I'll call it convex down. And it kind of makes more sense when you call it down because the curve is opening down and there's a relationship now with second derivatives, as we will see in a minute. So I can write the same kind of definition. I want to write a careful definition that encompasses the straight line also, the edge case. So no part of chord AB is above arc AB. So that's convex down. Okay, I'll have to be careful. Arc AB. So that is convex down. And we see under these definitions, a line, straight line, is both convex up and convex down. Okay, very good. So a line, we can just say, is just plain old convex. And we'll see that this makes sense in future videos when I talk about convex geometry. Line really is convex, you know, we'll see why. So that's our preliminary definition. If a function has this property over some interval, x1 to x2, or over the whole real line, if it has this property everywhere, yeah, then it's a convex function. Convex functions are very interesting, and you can have a lot of fun with them, as we will see very soon. Another way to look at convex function is like this. You take some arc and a chord. So here's my arc in blue. The chord is from point A to B. This is on the x-axis, little a and little b, and it's bounded by x1 to x2. This is our region. And if I draw anywhere here some horizontal line, then the point here, P, will be below Q always. Now again, we don't want to rule out the case of a straight line, so we'll phrase it in a way that doesn't rule it out, that'll take into account the edge case. So convex up, this is defined this way. Q is never below P. Okay, you can say that Q is always above P, but if you say that, you're going to have the edge case of a straight line. You know, it's going to be annoying later on. You're going to say, well, what do I do about straight line? Is it convex or not? And we want convex. We want convex straight lines. We want straight lines to be convex. So let's define it this way. And here, for convex down, we create the similar definition. Okay, so we have A and B like this, and the point A up here, point big B. Our chord now is this way, and I draw a line anywhere, horizontal line. And what do I have here? I have P on the arc and Q on the chord. The convex down means Q is never above. Q is never above P. So this is a convex curve. It's always turning in one direction. It opens like a bowl downwards on the interval of convexity from x1 to x2. And these particular curves are in fact catenaries, so they're convex over the whole real line. But anyway, this is the way to look at convexity. It's a simple property of curves. Many important functions are convex, and they're very, very interesting functions because they have some interesting mathematics that flow naturally from them. So let's begin to look at that. Here I've drawn a nice clean figure. This here is my f of x. It's convex up, the blue curve. And my interval of convexity is x1 to x2 from here to here. In fact, this interval can be as big as you like because this function's convex everywhere. So in red, I have drawn this trapezoid here. Okay, from point A up to f of A and then f of B down to B here. And right in the middle, I have this midpoint, A plus B over 2, and I can call this midpoint S. All right, so that's A plus B over 2. P is a point on the convex curve, and Q is a point on the chord. So here's my chord, and here's my arc. Now, let's see about this. This is very interesting because here Q is above P. My function is strictly convex, so it's not a straight line, so Q is going to be strictly above P, at least in this case, because my arc is a big one and my chord is fairly long. But if I take a very, very close A and B, let's say if I bring A and B very, very close together, you can see that Q and P is going to start to become very close to each other, sort of like the approximation of a derivative. So that's interesting. So I'll keep all these things in mind. All right, so let's think about this. What can we deduce from this figure? Well, first of all, we know the point, the length of SP, because we know the point P. This is S, okay, and so this length from here to P is F of the midpoint S here. So this length is F of A plus B over 2. So we know the length of this segment SP. But we don't know the length of SQ, not yet. But we know another thing we know, because we know from convex functions, that we know from the definition of convex function, we know that SQ is going to be bigger. Well, okay, I'll write it like this. SP is less than or equal to SQ. We know that this is true. It's not, Q is never below P, so SP is less than or equal to SQ. So Q never below P. This is followed from what we talked about before. So if we can find SQ, what is SQ? Then we have this interesting inequality that we can deduce. And maybe this is an interesting inequality. And in fact, it is a very interesting inequality. So how can we figure out SQ? Well, this is a trapezoid, right? So when you have a trapezoid, you have something like this. And you have two bases. You have base 1 and base 2. They're parallel, these two bases. And the midline of the trapezoid, so let's call this PQ. So what is PQ of a trapezoid, the midline? Do you remember? Well, it's the average of the two bases, b1, b2 plus b2 over 2. Okay, let me try to write better like that. Great. So, in fact, it's very easy to compute the length SQ. That's just the midline. This length here is from here to here. This is f of a. And this length from here to here, this is f of b. Yes? So that's f of a plus f of b over 2. Like that. And so SP less than or equal to SQ, this gives us the following very interesting thing. F of A plus B over 2 is less than or equal to F of A plus F of B over 2. So what's so interesting about this? Well, it turns out that this thing is like a master inequality. It is the inequality of many inequalities. Okay, this is like a master inequality formula. Okay, we will see what that means in a second. But this is really something very, very beautiful inequality. And it's true for any strictly convex up function. Like, okay. And now, before I continue, I want to examine the case. When can you have inequality? So when does this become equality? Well, I think there's two cases. Well, one case is when f of x is just a line. All right, and when f of x is a line, of course, the arc is going to be the same as the chord, and so choose any line. It doesn't have to be the midline. If I choose any line, PQ going or PQ to S, it's going to give me an equal PQ, and so the two SPQ SP will be equal to SQ for when f of x is a line. So that is going to be always true. But also when A approaches B and B approaches A, when they become very, very close to each other, then SP is going to approximately be the same as SQ, and in the limit, they will be equal. And we will see that this behavior here is exactly like the kind of behavior we see with inequalities like MGM and so on, that those things, they move from being inequality to equality. You get the equality case when the two numbers A and B are the same. So it's very, very interesting. Right, so let's look at some examples. Let me leave that up there and let's go through a few examples. But before the examples, I want you to do an exercise, and I want you to derive the inequality, the similar, it's not going to be the same, for convex down, for f of x is convex down. So I did the case for convex up. Here f of x is convex up. You now prove the similar inequality for convex down. So draw this picture for convex down, go through all the same logic, and do this proof for convex down. All right, now example 1. Let's take the function f of x is x squared. This is convex up. How do I know it's convex up? Well, there's two ways to know. One way is draw the graph and look at it. That's pretty acceptable in my view. Another way is let's take the second derivative. Second derivative of this is 2, and that's greater than equal to 0. That's convex up. So when you do a second derivative and it's greater than equal to 0, you have convex up. Or if you find the second derivative is less than or equal to 0, then it's convex down. And a straight line then is both convex up and convex down. Okay. So let's plug it into our master inequality equation. And we have A plus b over 2. The function is squared, less than or equal to a squared plus b squared over 2. So I'm substituting this here for f in here. All right, and what do I have? Let's take the root of both sides. A plus b over 2 less than or equal to square root a squared plus b squared over 2. That's very interesting. This should ring a bell. What is this? Well, this on the left is arithmetic mean, AM, and the thing on the right is RMS. So AM less than or equal to RMS. What is RMS? It's root mean square. So the root mean square of two numbers, A, B, is always going to be greater than or equal to the arithmetic mean of the same numbers. And this is true for what? Well, x squared is positive everywhere, but we're going to restrict ourselves to a range where x is greater than 0. Okay, so we don't have anything to worry about. It's convex in this range, of course, and this ends up to be true. So we managed to derive this inequality by examining the convexity of this function here. I think that's really amazing. And let's look at another example. Right, so continue along that thought. Instead of x squared, xp. Now, xp, this is convex up in the range where x is greater than 0, or the domain of this function is x is greater than 0. This is always going to be convex because second derivative is positive. Actually, it's going to be strictly convex. So let's see, where does this lead? Well, same thing. Let's go back up here and have a look at our formula. Let's write this thing down again. It's like this. F of a plus b over 2 less than or equal to f of a plus f of b all over 2. All right, where does this lead us? Okay, so this is a plus b over 2 power p, and that's less than or equal to a power p plus b power p over 2. And now I take the pth root of both sides. I get this, a p plus bp over 2, 1 over p. So this is arithmetic mean less than or equal to mean power of order p. Mean power, MP is mean power of order p. So RMS is mean power of order 2. I did a video about this, about mean power of order p. It's very interesting. There was a nice proof in this video, and I will leave the video in the video link in the description box. Okay, and you should watch it if you're interested in this. So this is another very pretty inequality that just flowed like magic from convex function. We had a convex function and poof, we get an inequality. So it seems that every time we have a convex function, we also have an inequality that flows from it. Example 3, let's look at f of x is 1 over x. So the first derivative of this is minus 1 over x squared. Second derivative is 2 over x cubed. So this is greater than 0 for x is greater than 0, yes? So that's pretty good. That means that this is a convex function, convex up. Convex up. And what does this give us? Well, I go back here and I use my convexity inequality and I plug this in. I have a plus b a plus b over 2, and this is inverse because my function is 1 over x, less than or equal to 1 over a plus 1 over b over 2. Now let's rearrange this a little bit. This is 2 over a plus b less than or equal to 1 over a plus 1 over b over 2. Yes? And I can flip this around a bit and I get 2 over 1 over a plus 1 over b is less than or equal to a plus b over 2. Okay, so that's my final answer here. And what does this mean? Well, on the left I have harmonic mean. That's the harmonic mean of two numbers, two positive numbers greater than 0. And the harmonic mean is always less than or equal to the arithmetic mean. So I have derived yet another of our favorite inequalities by using a convex function. That's incredibly beautiful, I think. It's just really remarkable. And let's look at another one. Example 4. Let's look at another one. Example 4, let's take f of x is log x, natural logarithm of x. So f prime is 1 over x, and f prime prime is minus 1 over x squared. So this is actually negative when x is above 0. So this function is convex down. Okay, so f of x is convex down. Well, what are we going to do here in this case? F of x is convex down. Well, I asked you to do an exercise where you had to prove something for convex down. And, well, I hope you do that exercise. I'll just write down the result. When f is convex down, I get the opposite inequality here. F of a plus f of b. This is now the other way around. You could have probably guessed this. This is the other way around now. And let's use this with log. So I have log a plus b over 2 greater than or equal to log a plus log b over 2. But I can use some log magic and combine these two and get log. Well, the 2, I can bring the 1/2 here inside and put the a and b together. So I have a, b, and then square root like this. Now I take away the logs. The a and b are positive numbers. We have chosen x greater than 0 as our domain of convexity. Okay, so I end up with a plus b over 2 greater than or equal to root ab. And I'm sure you know this. Let's rewrite it in a more canonical form, a plus b over 2. This is geometric mean less than or equal to arithmetic mean, the famous AMGM inequality. So AMGM follows from convexity of the log function. I think that's truly amazing, truly amazing. Now, in all these cases, in all these examples, in all these cases here that we looked at, f of x was strictly convex. So the only way to get equality, in here, like in these inequalities, the only way you can get that equality is when a approaches b, or b approaches a, and they become very close to each other and actually equal to each other. That's the only way, because in this case, none of these cases do we have straight lines. All right, so we were careful about this. So, and you notice that the convexity analysis of this gives you a really nice explanation of why you can sometimes get equality and why that only happens when a equals b. I think that's really, really beautiful. So now I'm going to leave you with some suggestions. First thing you can try is choose your own functions and determine if they are convex up or convex down on some domain, and investigate whether or not you can derive some interesting inequality from your choice. And if you can, send it to me in a comment. Tell me about it. Another thing I suggest, which is kind of interesting, is to choose a function that's linear, mx plus k. It's convex, both convex up and convex down. So what happens in this case? Well, it's actually kind of interesting. Try to repeat some of the analysis that we did and tell me what happens to see how it goes with this. I did this, well, I've done both of these things, and yeah, it's kind of interesting. It's really fruitful thinking. There's quite a bit to discover and play around with here. Well, that's it for today. I hope you like this. I think I'm going to do another video on convexity. There is so much to talk about, and I hope you liked how all of your favorite inequalities can flow naturally from one master mathematical principle called convexity. I think it's really dramatic, beautiful, remarkable. So click like and subscribe, of course. And I will see you next time.